Welcome to The Explainer. Today, we are diving deep into one of the hottest topics in the shipping industry, using methanol as fuel. We're going to get into the nitty-gritty of the engineering and the safety systems needed to make this a reality, using the WinGD XDFM dual-fuel engine as our guide. All right, so here's how we're going to break this all down. First, we'll look at why shipping needs to change in the first place. Then, we'll see why methanol is such a strong candidate. After that, we'll tackle the unique risks that come with it, look at the entire onboard system, and finally, we'll zoom right into the heart of the machine, the engine itself. So let's start at the beginning. Why are we even having this conversation? Well, the entire global shipping industry is under massive pressure. There's a worldwide mandate to clean up its act, cut emissions, and find greener ways to power the global fleet. And this right here really gets to the heart of it. The International Maritime Organization, or IMO, has laid down the law with some really aggressive emissions targets for 2030 and 2050. These aren't just suggestions, they are hard deadlines that are forcing everyone to innovate, and fast. And that's exactly why methanol is looking so attractive. Okay, so we know the industry has to change. But out of all the different options out there, why is methanol getting so much attention? Let's take a look at why it's considered such a leading contender. Well, from an environmental angle, the argument is pretty strong. For starters, it just produces less CO2. Plus, it's basically sulfur-free, which is a huge deal for ships operating in those super strict emission control areas. But the real game changer? It can be made from renewable sources, creating what we call green methanol. That offers a genuine path to a carbon-neutral future. But, there's no free lunch, right? And here's the big trade-off: energy density. Methanol is way cleaner, but it just doesn't pack the same punch as old-school fuel oil. What that means is, to travel the same distance, a ship needs to carry a whole lot more of it. And this number, 2.5 times, has massive consequences for anyone designing a ship. You need 2.5 times the tank space to get the same amount of energy. That's a huge chunk of real estate on a vessel that could otherwise be used for paying cargo. It's a fundamental challenge that has to be solved right from the drawing board. Now, obviously, you can't just swap out one fuel for another and call it a day. Methanol comes with its own unique set of safety challenges. So before you can even think about using it on a massive scale, you have to understand those risks and engineer your way around them, and it really boils down to these two core problems. First, its flash point is super low, which means it can create flammable vapor really easily. And second, if it does catch fire, the flame is almost invisible in daylight. You could have a serious fire raging and not even know it's there. This number right here is absolutely critical: 11 degrees Celsius. That's about 52 degrees Fahrenheit. Think about the deck of a ship in a warm climate. The air temperature is almost always going to be higher than that. So you have to operate under the assumption that a flammable vapor could be present at any time. That changes everything about your safety approach. So to manage that constant risk, engineers basically create a map of hazardous zones on the ship. You have Zone 0, which is ground zero, inside the tanks and pipes. Then there's Zone 1, which are the areas right next to potential leak spots, and Zone 2 is a buffer around that. Each zone has its own super strict rules about what kind of equipment you can use to avoid any chance of a spark. The whole prevention strategy really boils down to a 3-step playbook. First, you control the vapor itself, usually by pumping an inert gas like nitrogen into the tanks to push out the oxygen. Second, you are relentless about getting rid of any potential spark. And third, any piece of equipment that has to be in one of those zones must be certified as totally explosion-proof. And remember that invisible flame? That means your normal smoke detectors are useless. Methanol burns too clean. Heat detectors are often too slow, so you have to turn to specialized tech. You use infrared detectors that can actually see the fire's radiation, and vapor detectors that can sniff out a leak long before it ever finds a spark. Okay, we've talked a lot about the risks and principles. Now let's see how this all comes together in the actual hardware. We're going to trace the path of the fuel, from the moment it comes aboard all the way to the engine. And we're not just talking about a simple tank and some pipes. This is an entire complex ecosystem. You've got the bunkering station, special inerted tanks, that double-walled piping system, a dedicated prep space, complex valve units, the whole shebang. One of the most critical parts of the design is isolation. All the important gear, the pumps, the filters, they aren't just sitting in the main engine room. No way. They're housed in their own dedicated, gas-tight room.
It's basically a fortified, safe room for the fuel system designed to contain any possible leak and keep it far, far away from everything else.
This is probably one of the most important safety features. Every single pipe carrying methanol is actually a pipe inside of another pipe. The space between the two is constantly checked by sensors. So if that inner pipe ever springs a leak, the fuel is caught by the outer one. An alarm goes off and the whole system shuts down instantly. It's brilliant. All right, we've safely delivered the fuel to the engine's doorstep. Now, let's step inside and see how the engine itself handles this stuff safely and efficiently. See, for methanol to burn properly, it needs to be injected under insane pressure. It gets to the engine at a pretty low 13 bar, but then it hits the methanol booster unit, or MBU. This thing acts like a massive pressure amplifier, taking that fuel and blasting it up to around 600 bar. That ensures it vaporizes perfectly for a clean, powerful combusting. And that same idea of multi-layered safety we saw with the ship's piping, it gets applied with even more intensity inside the engine. It's called the double barrier concept, and it's the golden rule. No single point of failure can ever be allowed to cause a leak. So how do they do it? With two distinct layers of protection. Barrier 1 is physical. It's that same double-walled pipe concept on all the fuel lines. Barrier 2 is a bit more clever. It's hydraulic. Inside the MBU, they use carefully pressurized sealing and cooling oils to create a fluid barrier. This makes it physically impossible for methanol to mix with the engine's lubricating oil, even if a seal fails. So when you put it all together, the clean burning nature of the fuel, the strict safety zones, the isolated hardware, and this incredible double barrier system inside the engine, what you get is a really complete, thought-out solution. It's a technical blueprint that tackles both decarbonization and safety head-on. Which really leaves us with one big question. Are we looking at the future of green shipping right here?